So this last exercise is designing lead lag compensator or lag lead compensator. So actually, what's the difference between lead lag or lag lead compensator? Basically, you need to combine the lead and lag compensator. Well, in your PDF I gave to you PDF 4. Here they are explaining them, and basically they said this terminology they're using it here. When they say lead lag compensator, or when they say in this case lag lead compensator, so you design first the lead, then the lag, okay, which is the PD, and always recommended to I'm telling you, so always recommended to start designing the lead, then the lag, as we did in our previous exercise 7. We started designing the PD, then the PI. So here start designing the lag or PD equivalent to PD to satisfy the transient requirement. Remember in our exercise 7, to satisfy the transient requirement of the system, overshoot, peak time, settling time, etc. Those transient requirements basically are overshoot, rise time in case needed, but usually we use overshoot, peak time, and settling time as design requirement and transient requirement. And then you later on you design the PI to satisfy the steady state requirement, which is basically one requirement, which is steady state error. Those are the main requirements we use to design our controller. So then start always with my recommendation with the lead or PD, then lag. Okay. Alright. For this system, so that the system will operate with 20% overshoot. Here I did the solution, so just for the sake of time, so we can go faster. Will operate with 20% overshoot and a twofold reduction in settling time. So design the lead lag compensator in a way that this system will operate with a 20% overshoot and twofold reduction in settling time compared with the non-compensator system. So this is using the CISO tool with an overshoot of 20, I can get the settling time and the gain K, for example. So using the CISO tool at overshoot of 20, using the CISO tool or the Control System Designer app, I can find I get 20% overshoot in case of K equal to 100. And this is, it will give settling time of 2.17 and steady state error equals 0. Keep in mind for a step, of course, for a step steady state equals 0 because it's type 1. What if I ramp? So because here they said the compensated system also will exhibit a 10-fold improvement in steady state error for a ramp input. So for a ramp, the story is different than for a ramp. How to find the steady state error? We said doing by hands, don't do in MATLAB. It's not easy to get by MATLAB. So then you use our table, steady state error 1 over kV for a system of type 1. And kV, limit when s tends to 0 of s, the open loop transfer function here, which is in this case, that's my open loop transfer function. So then you can get kV in this case, and therefore you can get the steady state error for a ramp for the uncompensated system. Of course, K is the one we get that gives 20% overshoot. So if you do, you get steady state error 0.3 for a ramp input. So my design goal is to have a compensator, to add a compensator, lead lag compensator, that leads to 10-fold reduction in the steady state error. Therefore, and this will be my design goal. 1 over kV new, then my kV new design goal will be 33.3. And this will be used for designing a lag compensator. But first, we said we start by lead to meet the transient requirement. So then, let's design the lead to meet the design requirement. I have two design requirements. overshoot 20 and a settling time of half of the old settling time. The old settling time, which is for the uncompensated system, we find it using the CISO tool, and here they said the compensated system should reduce the settling time by twofold. So that's why it is over 2. The new settling time is over 2. So to design the lag compensator, I use the lead compensator. I use the settling time half times the old settling time, so I can get sigma, and it will be used with the MP for designing the lead compensator first. Okay, those are the transient response, the transient requirement for me, the settling time and the overshoot. So how to design lead compensator? We are familiar with, of course, a lead, so the 0 will dominate. So you can do the hands-on method, or I told you recommended to go directly with the CISO tool and pick a 0, then a pole to the left of it, make sure, otherwise it becomes a lag. But here I did it the calculation method, so which you are familiar. You find omega d, and then later on you find the theta, the angle for each poles, and 0 if there is. You assume a 0, and you find the angle for that 0. Sum of zeros angle minus poles angles equal to 180. You find the pole angle, then from the pole angle you deduce the pole, and you get that pole. Alright, that's it. Then the lead compensator, assume 0 of 8, and I get that pole that satisfy my transient requirement. Then now you need to adjust K using the CISO tool to satisfy the requirement, the transient requirement. So so we're always we need the CISO tool. It's not like completely by hand. If completely by hand, complicated, so more time. So, but I'm using have a little bit calculation, little bit the CISO tool, combining them together in a clever way. But you could still completely use the CISO tool. Just pick a 0 and a pole to the left of it, as I will show you in a while. Alright, let's go and design this lag compensator then. Alright, this lead compensator. Very cool. So now my system is, that's the system I'm using. So it's OLTF5 open loop transfer function 5. So alright, settling time and overshoot design required. Overshoot or settling time less than, I forgot, let's go check, less than 1.08. Alright, and and an overshoot of 20. Of 12. This is my design requirement. I need to be here at this point if I want them to be equal. Keep in mind again and again, this is only valid for canonical systems, so its starting point should be around it. So to satisfy my transient requirement, I decided to design what? A lag compensator, a lead compensator to satisfy this transient requirement. First, I can change the gain to have my overshoot, which I find for you but this is not necessary now. We don't need it for now because we already did the calculate. We already did it. So, and I based my things on. Let me put it directly 200. But this is of course the first step we need to work on. All right. So then in here I have 20, and my settling time is this one. This is uncompensated system. Well, I cannot say it's completely uncompensated because it is with proportional controller, which is fine. Okay, so it is compensated, but so now I store it as design one. So I need to add lag compensator to satisfy my transient requirement, which is 20% overshoot and less than 1 peak time. Settling time actually not less than 1.08. Basically I should be here. Alright, so now adding lead compensator 0 and pole. Where do I want to put the 0? I decided to put the 0 here. Okay, so I can put my 0 here, or I could put it here if I wish. So I prefer now to take a different design. I'll put it here. So I click on it, so I find the editor one way, or you can double click and add it, or right click and add the 0 as you wish. But I use this interactive. I click the 0. Remember, it's a lead compensator, so the 0 close to the imaginary axis, and then I change my point. I fix my 0 in here. Okay, so see how it shifts my design. So now when I want to put my pole, so the pole, now I take the pole, and that's my pole. Okay, I shift it to the more to the left, and it seems like here is alright. Let's see the overshoot, and basically two requirement: overshoot and settling time. Less than 108 or 108, and overshoot of 20. So clearly we don't have overshoot of 20. Less than, if you can go less than, then you keep it this way. If you wanted 20, exactly 20, then means it's not, I need to go overshoot more. But in general, it's acceptable to have less, but less is more, so you are more safe. But if you want to go in deep and study more, so you can look to the control effort signal, and you will see if you don't allow overshoot, you may have a high control effort. So better to allow overshoot in your design. Depends in the system itself if this is acceptable, or what's your design requirement as a control engineer. What's your design requirement? So in this case, they asked me to have overshoot of 20, assuming that's the case. So then if I go this way, my overshoot, alright, but I'm increasing my settling time, which is 108. So now I'm 109. So you see, I should be in the white zone, still in the white zone. It seems like the location of the 0 here is not alright. So that's why if you don't have experience, maybe, okay, I'm putting my 0 here, so then maybe I need to change a little bit my pole. Keep changing my pole, because I assumed I fixed my 0, and that's a 0 that I want. Otherwise you can change the 0 and see how the thing will reshape. But because I want to just change one variable, which is the pole, so I decided to keep the 0 here and keep changing. Hopefully maybe I get better things. So right, so maybe So it seems like this zero location really doesn't help on providing overshoot, so it really excites your actuator. You need putting the zero this way. This compensator will provide high control signal and therefore less overshoot. So then maybe it's a good way to reorient your zero. See, I reoriented my zero. My zero now it's at 11. It gives me other overshoot. Let me zoom in this interesting zone and see what's going on. So now maybe I change my pole if I wish, or I could also keep changing the zero. Here I have 19, but I have 1.78 settling time, so I'm not satisfied my requirement. So the zero will zero near. So now near the imaginary axis will make the system what faster, because it will dominant. It is dominant now. So then I become faster, because we know the effect of derivative is to improve the to make the system faster. So then here, when it comes interactively, when you are playing interactively, you are not playing without sense. So there is a sense, there is meaningful things you need to think about. So then maybe I decided to even go more. So here it seems like I'm at a pole and zero, or so they cancel each other. They create instability of my system in my system. So what I'm changing actually the pole, not the zero. The gain. It looks like I'm clicking on the gain. Okay, but I don't want. I want to click on the zero itself. Okay, I'm still clicking on. See, the gain is still changing, but not the. Okay, if that's the case, let's shift the gain and move the zero. Alright. What's this gain, which is very high? Alright, let me go here and put a gain of 1. And restore the view of the system. Okay, I will again reshape. See here, I'm reshaping it, so it looks like I'm fine. So let's change the gain. Your pole, by the way, is here. It seems it's coincident with a pole or zero, I'm not sure. But let's see if I reach here. Okay, 22, 20. Okay, this 18 point something. 21, maybe I can do it by hand. So let's say controller C. One important thing, because this would make, just let me unify the things. Now my compensator is the one that's here. So maybe I decrease it a little bit. maybe. Okay, 20 and 1.15. 1.15, let's see, you need to be 1.08. Keep in mind, this is a lag compensator. Later on, when you add the when you add the lag compensator, also the system will slow down. Therefore, it's better to over design the settling time itself. So then be around 1 or so. That's 108. So here, still seems like I need to retune or find maybe. What if I go more? Oh, okay, give me more overshoot. Alright, so I return the value to the one you end up on, and maybe change the pole. So change the pole. This is what the effect of pole will slow down the system. See, then maybe so then you go with it in this way. Alright, so you put it maybe very far away. What if I increase, like here, minus 45, maybe I put minus 50. 1.1. Okay, so now I can change the gain again. 107. Okay, I can, if I wish, also, right, and this is, I change my pole a little bit, even more, if I wish. You see, it has no effect now because it is somehow negligible. Okay, so now so 105, 108, 20.5. So I can stick with this design for my lag compensator, and I store the design as well. This is the lead compensator. This is my lead compensator, and I readjust the gain to fill the requirement. Or so by doing it, sometimes like it takes even time with me by tuning it this way. So yeah, it takes some time, as you see, to get it. So then if you have your system here, you make it in a program in MFI and MATLAB, so in a way you can just plug and play directly. You change just the arguments of your function, and you get directly the result. You can get directly a PC by a MATLAB function that you could make yourself. Then maybe it becomes faster to do the analytical way in this sense. Okay, and a lot of researchers they work this way. So just they have their own function and they get the result directly. So maybe it becomes faster than retuning and go and back. And later on I'll implement this for you and show you I can actually get same result. So now, so I don't want to use this. Also, let me delete the design tool, and I don't want to use this controller. Let me delete it as well, and add the lead that we designed just now in our calculation. So 8483.7. So I have 8 and I have 483.7. Good. And this is for which gain? This is my 0 and pole. and this is for which gain? Let's keep the gain as it is. See if it is 17, 1.1. Maybe I need to go more, up to 20. So maybe 19.3, 22, 21, 21. So I can do it manually. 3, so I decrease my gain to 400 maybe. Doesn't really affect. 300, 20.9, 33. Is it 1000? 20.7. So I need to go less than, so to 900. Doesn't affect. 700, a little bit. So maybe 19.5. Okay, this seems good. Overshoot of 20 less than and 1.606 less than 1.08. Fine with this. That's the one I found by calculation. So you see, and then I retune the gain only. Alright, so now I need to add the lag compensator on it to satisfy the overall requirement, basically the steady state error. So then the lag compensator is equivalent to pi. So then the pole here is here close to the imaginary axis and the 0 to its left. Then k nu, you need to find kv nu. Remember, it was here finding kv nu, which is equal to 33.3. How did you find it? By dividing the old steady state error over 10. The old steady state error for a unit ramp, we find it by 1 over kv, and kv is the limit when s tends to 0 of what? Of the open loop transfer function, and this is important, open loop transfer function. So then kv nu equal limit when s tends to 0, s g of s, where g of s, if you wish, is the open loop transfer function. Alright, so then this kv nu, which is 33.3. So we will be using it to find the relation between ZC and PC. Yes, we are here. So then take the green color. Alright, so I take the green color. G lag, okay. So then kv nu limit when s tends to 0 of s times the open loop transfer function. And so you see, what is the open loop transfer function now? It is the lag compensator and the lead compensator. Well, it seems like when I did my simulation, that's my lead compensator. Here, the one I found, is it the same? Yeah, 31500, and the one I get here, 3, very similar. What are the design requirements? I get 20.9 and 103. Okay, so here I get 19.8, 106. Alright, which is fine. Then let's keep it this way, because now this I did the calculation here with that value, which is also fine. Yes, so then this is your lead, this is your lag, and this is your plant. So in your open loop now you have the lead lag compensator and the plant. And KV new, it's known, we found it before. So then limit when s tend to 0 of s times this, because it's type 1 system, of course, so no. Then we can find the relation between ZC and PC. And so we have the relation, we assume PC close to the origin, then we get ZC. That's why calculation is better in the sense quickly going somehow, especially here. It doesn't take a lot of effort, but you need to understand the theory behind. So, alright, so this is important, lead lag plant. And we designed then a lag compensator to satisfy the steady state error, which will reduce it for a ramp, of course not for a step. For a step, steady state error is 0. Then we add this lag compensator and we readjust the gain to satisfy the overall requirement. Alright, so then 0.036 and 0.01. Alright, just verify, yes, 0.036, 0.01. So that's my final controller, but we need to readjust the gain, take it to the design requirement, 20, 20.3, 1.04, so I am, this is I consider as acceptable, okay? And this is my final controller that satisfies my requirement. So basically now you can design any controller, lead lag, PD, PI, using CISO tool, and this is what we call controller design using root locus. So in this chapter, in addition to this methodology using root locus, you learn how to design lead lag controller and how they are important in controller design. Okay, maybe I didn't point out for or maybe I pointed it out, but just I like to remind about when we design PID controller. So our PID controller was, if you remember, PD times PI, and yeah, I mentioned it here. So you see, it is, that's how it is. Okay, that's it for this exercise and for this chapter in general.